Hi, my name is Mathieu Gaillard and I'm a PhD candidate at Purdue University. Today I'm going to present our paper, Automatic Differentiable Procedural Modeling. To start, just a quick introduction about procedural modeling. It is straightforward. The procedural model is a program that takes as input some parameters and automatically generates a virtual asset. If you change the parameters, what you get is another variation of the model, right? The issue, though, with procedural modeling is that any edits on a procedural model must occur in the parametric space as opposed to the 3D space. Otherwise, you lose the procedural nature of the model. Yet, users are most comfortable expressing their intent in the 3D space, as it is tremendously easier to directly change the object rather than having to tweak some sliders. What would be nice, though, would be to have an automatic way of doing this. That is why we present Automatic Differentiable Procedural Modeling, also known as ADPM, a system that can automatically translate edits made on the 3D model back to the procedural parameters. For example, with this procedural sofa, the user can select the backrest, shrink it, and the system automatically updates the procedural parameters to match the edit. In this case, the width of the sofa was decreased to match the desired size of the back seat. All of this is of course happening in real time. This may not seem to be new in the sense that it's already been seen with inverse kinematics. However, our system works on a class of procedural models versus a single object. Furthermore, with our system, once the graph is generated, there is no need to rig the model. It's all automatic. We claim the two following contributions. First, a node-based procedural modeling system that allows interactive editing even for non-experts. Second, if the user requests an edit that is underdetermined and has degrees of freedom, our system can provide a few suggestions. There are three main categories of related work. The first category is procedural modeling and representation. I refer you to a survey paper from Smelik et al. And for more recent software for procedural modeling, of course, there is Adobe Substance 3D Designer, which is based on a node graph. Our system also uses a node graph, but it extends it and does not require the end user to know about it, as all the model editing happens in the viewport. The second category of related work is inverse procedural modeling, where the goal is to find a procedural model that fits an existing geometry. The first paper is about interactive editing of a procedural model. The second paper, which is also from our team, tries to use a genetic algorithm to create a node-based procedural model. Our method is similar, but it focuses on local edits. The third category of related work is auto-differentiation. Our system uses Casadi, but PyTorch and TensorFlow are also frameworks that are extensively used for auto-differentiation of neural networks, for example. The second paper, Match, is methods that can automatically convert a photo to a procedural material graph using auto-differentiation. Our method extends this concept to a general procedural node graph generating 3D geometry and combines it with interactive manipulation. Perhaps the most interesting related work are these two papers, as they tackle almost the same problem. The first one was published a year ago at SIGGRAPH and is about interactive editing of parametric shapes. And the second paper is actually also presented at Eurographics this year. It's very interesting because it's the same problem, but different approach. I really encourage you to have a look at it. Before we begin, just a quick word about the procedural representation we use. It is a node-based representation implemented in Blender. So here on the left, you can see one of our procedural graphs, and on the right is the result. The typical workflow we target is that first, a technical artist designs the procedural model. Second, the end user can retrieve and edit the procedural model without knowing its underlying implementation. Here is an overview of our system when editing the procedural model. As you can see, it works in a cycle. Given the input parameters and the definition of a procedural model, we can generate the corresponding 3D model. Then the user makes a modification on the 3D model, and finally our system tries to match the edits by updating the input parameters, etc., etc. What is new in our system is that in parallel to the procedural graph, we have a differentiable representation of the procedural model that accelerates optimization when matching the end user edits. This slide is about the formulation of the problem we are solving. During the forward pass, we keep track of the position of oriented bounding boxes of components of the procedural model. Then, to make an edit to the procedural model, the user applies an affine transformation on one of the components. And finally, our system will try to change the input parameters to match the edit made by the user. Here is an example of an edit made on a sofa procedural model. You can see the bounding boxes of each subpart of the sofa. We click on one in the middle, which corresponds to the seat cushions. Each bounding box in the procedural model has a unique identifier so that we can keep track of them. This one is called double seat cushion. Now we scale it and make it smaller. Our system will try to modify the procedural model so that the double seat cushion bounding box matches the target set by the user. We use regular computational optimization, no magic involved. The cost function we try to minimize is simply the sum of square distances between the corners of generated and target bounding boxes. And here is the result. And it is fast, thanks to our proxy differentiable representation of the procedural model. Here is an example of how our system works. On the left, we have our procedural graph, which upon execution will generate first the 3D model scene tree, so far nothing new, and second the proxy differentiable representation of the model, which is a copy of the scene tree with objects substituted by oriented bounding boxes. These oriented bounding boxes are made differentiable using a differentiable type. For those who are not familiar with auto-differentiation, it is implemented as a type in programming language like float or double, except that it tracks all the operations that are made and you can efficiently compute the derivatives afterwards. It is the basis of deep learning frameworks like TensorFlow and PyTorch. When we execute the generate seat nodes, it adds the seat to the 3D scene tree. It also adds the corresponding oriented bounding box in the proxy differentiable representation. Like regular scene trees, between each object and its parent, there is a transformation matrix. In the proxy differentiable representation, it is the same, except that this matrix is also made differentiable using an auto-differentiable type. When we execute the generate legs node, it adds 4 legs to the 3D scene. It also adds the corresponding oriented bounding boxes in the proxy differentiable representation. Note that for the moment, legs are not attached to the seat, so their parent is still the root. When we execute the attach legs nodes, the seat become the parent nodes of each leg. This modification is also reflected in the proxy differentiable representation. After execution of the procedural graph, you can see the result. And now, if we want to know the position of an oriented bounding box in the 3D model, in the proxy differentiable representation, we multiply all the transformation matrices from the root to the bounding box, and this way we know the position and derivatives of the box. Just to formalize what we just saw, after the edit is made, on one side we have the position of the target bounding boxes S at, and on the other side we have the position of the procedural bounding boxes G. Our objective is simply to minimize the distance between these two sets. To solve our optimization problem, we use a second order method that converges very fast. That is LBFGSB. We can afford to use it because the set of parameters is small, and it is also very nice because it works with bounds on parameters. To accelerate computation of derivatives, we build a proxy differentiable representation of the scene tree while evaluating the model. Finally, since evaluating the gradient of our objective function takes less than a millisecond, we take advantage of that to run some flavor of global optimization. Now, a very interesting question. What happens if the edit requested by the user is underdetermined and has degrees of freedom? Our optimizer can detect that the edit is ambiguous and will try to explore the region of optimality within a budget of time. Finally, it will make a couple of suggestions to the end user. Following will be examples of configurations recommended by our system if we move the top cube up. In these slides, we show that our system can detect when an edit is underdetermined and can make various recommendations, all of which satisfy the edits in a different way. Additionally, our system is able to cluster and order solutions together in order to make it more predictable for the user when reviewing different solutions. Very quickly on how our optimizer works. When we reach an optimal configuration, to detect if the solution is underdetermined, we look at the eigenvalues of the Hessian. If one is close to 0, it means that locally the objective function is flat and there might be other optimal solutions around. Then we use a method inspired from Bayesian hopping, which essentially is like simulated annealing, but using the gradient to speed things up. What it does is that it takes random jumps from the region of optimality and then runs some local optimization to make it back to the region of optimality. If you repeat the process many times, essentially what you get is a sampling of the region of optimality. Conceptually, you can see it like if we throw a marble on the objective function and we look for attractors of this complex system. Finally, among all solutions we get, we extract some of them that are interesting, like we just saw in the previous slides. Also, we have a heuristic that finds clusters of solutions and order them for the user to review. This will be shown in results. First result is the sofa, which is an example of furniture. This is an important property about procedural modeling in general, but I want to insist on the fact that it applies to our system. Since the procedural model encodes the shape and input parameters are bounded, the result of any edit, even a silly edit, will give you a valid model. In other words, nothing can go wrong. Here we show an interactive editing session with the sofa. Next is a typical example of a model that undergo an underdetermined edit. It is a stool with an object on it. If we move the object up, then we can either make the seat thicker or lengthen the legs. This one is the solution that changes parameters the least. This one is the solution that changes parameters the most. This one is the solution that adds a constant value to all parameters. This one is the solution that keeps the proportions the best. This one is the solution that keeps legs the same 8. The succulent example is showing the result of our scattering nodes. The editing demo was already in the introduction. The robotic arm is the typical example of a model that has non-linearities. If you want to point the end effector at something, you will have to change all variables. Of course, manually it's not possible. Besides, it shows that our approach is generic and can give results similar to inverse kinematics. The centipede is just a model with many parameters. In this example, we constrained all legs to touch the ground and we moved the underlying terrain. This table shows a performance breakdown for each of our examples. The key takeaway is that the system runs at interactive time. Executing the procedural graph and displaying the 3D models takes up to 500 milliseconds. The time needed for local optimization is up to 12 milliseconds. Determining if the edit has degrees of freedom takes up to 5 milliseconds. And then exploring the region of optimality can take up to 6 seconds. For validation, we ran 2 user studies. We ran a qualitative study with one-on-one interviews with 5 users. The objective was to assess whether our system allowed non-experts to do 3D modeling quickly and efficiently. We also ran a quantitative study where the goal was to check if users are interested in having multiple suggestions in case of an underdetermined edit. The answer is obviously yes. That leads us to the conclusion. We introduce a new procedural modeling system that lets the user manipulate the generated output directly in the viewport and propagates edits back to the input parameters. To make this everything real-time, we use a proxy differentiable representation of the procedural model, which significantly accelerates the optimization when matching edits made by the user. In terms of limitations, it is mainly about the formulation we chose to use. The level of edits we allow is on the object level versus the vertex level, like in the related work. The consequence is that the edits are coarser, but significantly faster. That is the trade-off we chose, and it gives us more flexibility with optimization. Like with other papers from the related work, we do not support integer parameters, only continuous real valued parameters. The reason is that it makes optimization very complicated, and we did not look into this issue yet. Finally, there is no automatic procedure to convert a normal graph to a differential graph. As a future work, we could add a semantic meaning to parameters to help our system to make relevant suggestions, like theta is an angle in degrees and the width is a length in meters. This information would be used to improve recommendations. To further improve the speed and reactiveness of our system, we could also implement a multi-threaded optimizer. We did not experiment with other editing metaphors other than the Blender 3D gizmos. Finally, our clustering and ordering of samples in the region of optimality works best only if the region of optimality is a 1D manifold. Using a nonlinear PCA would probably allow us to determine the dimensionality of the region of optimality, which could be used to provide a better UX for choosing a solution to an underdetermined edit. Thank you so much for your attention.